Thank you very much. So today we would like to talk about enabling seamless production with predictive maintenance and also how this approach can be relevant for you. So first we will have a short introduction, quickly about our company, then about predictive maintenance, then the main topic will be the use case, so how to enable seamless production. And we will conclude with one word, how is this relevant for your company? What can you talk out of this for you? So, a bit about our company. We are the Adastra Group. It's a worldwide company with headquarters in Toronto, Canada. We have several local companies such as Adastra Germany here in Germany with also offices all around Germany. In total, we have 2,000 employees worldwide, 150 in Germany, and besides the strong European focus, we also have nearshore capabilities in Eastern Europe or in Thailand offshoring, so we try to find the best package for all our clients. And what do we do? If I have to summarize it in one word, it's data. We love data end-to-end from the beginning to the very end. So can be consulting, can also be data-driven approaches, digitalization, and the end-to-end implementation. So really, how can we get you the best out of your data? And this is how we measure our success. We measure it with your own client success. And speaking about the use case, my colleague Simona will take over.
Thank you, Johannes. So nowadays, manufacturing industries have to deal with an always increasing degree of complexity. For instance, in the production lines, the processes are complex and always interrelated with a lot of dependencies. And in this scenario, if one particular machine in the line fails, the whole production is affected and the line is severely injured. And in the worst case scenario, the whole production needs to be stopped. And in order for an industry to succeed and have a seamless production, proper planning is key for success. And how can industry plan and try to have a proper and seamless production? Well, on one side, one could minimize the downtime of the machines, and on the other side, one could try to optimize the processes and the whole production as a whole. But in order for this to happen, it's absolutely important to have a specific and a good overview of what is happening in the plant at any given time, and try to have the most reliable prediction of what could happen in the future in the plant. In this context, predictive maintenance plays an important role. But what is predictive maintenance? Most of you know it's like we could think about it as a set of techniques that one could employ in order to understand what is happening to a specific, and what is the status of each of the machines that are employed in a plant, and working on top of this knowledge of the status of the machine, try to predict when, for instance, maintenance is due, and for instance, in order to change some of the parts of the machine before they break. But what is needed for predictive maintenance? Well, first of all, it's important, as we said before, to know the status of this machine at any given time. And how do we do that? It's important to have data. So sensors attached to each of the machines are important and help us gather this information. Once we have all this information, one could deploy and use multiple models, and according, of course, to the different machines and the different scenario that one has in the plant. And also of great help could be having a robust architecture framework that allows to scale, allows to scale, so it's not just used for one single machine, but for the whole plant or multiple plant if an industry has more. But why is predictive maintenance important? If we look at the graph on the right-hand side of the slide, the different area correspond to different contribution to the total cost of maintenance. And we can see on the left-hand side here, we have the case scenario where simply a machine is let run, it runs until it breaks. But in this case, once it breaks, first of all, there is a huge downtime because maybe we need to, the people need to understand what part of the machine has broken, and in breaking this part of the machine might have damaged also other part of the whole machine. And also, if we wait for the machine to break, we have no idea when this failure can occur. And of course, we are not ready to take action right away. We need to wait for the people to come to do maintenance. On the other side of the graph, on the other side of the graph, so on the right-hand side here, we have the opposite scenario. So if we are scared to let our machine break, we want to schedule maintenance for our machine so that we are sure that it will never stop because it breaks, it would never fail. But this also has a cost that is not negligible, because every time we schedule a maintenance, the machine needs to have some downtime. And in cases, for instance, in continuous production, this has quite a big effect. Also, if we keep making maintenance, so we keep have maintenance, we keep changing parts of the machine that might still be perfectly well and might still work properly, and so therefore also the cost of spare parts is not negligible anymore. And in this specific scenario, predictive maintenance is actually quite useful because it allows us to find the sweet spot between the two opposite scenarios. So on one side, we want to try to have maintenance the least amount of time as possible, so that we have the lowest amount of downtime we can. But on the other side, we have to try to find the perfect time before the machine breaks and causes severe damages. So we would like now to present one case how we managed to seamlessly to help our client Magna to improve their production and implement successfully predictive maintenance for one of their machines. So our client is Magna International, that is a Canadian-Austrian automobile parts manufacturer, and it produces components for the automotive sector, and their clients are car manufacturers all over the world, and they have several different plants spread around the globe. In particular, for our use case, we focused on a specific machine that they have at different plants, and it's what you can already see on the picture here is a 1,200-ton transfer press. This gigantic machine is used semi-regularly, and I mean, you can really see the size of this machine. If you check, like, this is almost as high as the ceiling of this huge production plant. It's a big machine, and it's composed by several different parts that are interconnected, so it's important to understand how all the different parts work and how they are related to each other. And initially, for our study, we focused on the oil tank that is present on top of this machine, in particular in the top here, that is in the jug, or called the crown of the press. So once we started working with our customer, we focused in particular on this oil tank, and the most important things were the oil level, the temperature of the oil, and also the quality of the oil itself. Why is this important? Because if the oil level, for instance, is not nominal, meaning that it goes below a certain threshold, the machine cannot work properly and needs to be stopped for the tank to be refilled. Because if the production keeps going, so if the machine is not stopped, it might incur in severe failure that might block the production for a longer time. Initially, before we started our work with them, this refilling of the oil tank was done manually, and it would cause sometimes longer downtime because the information about the oil level was present just locally, and once it would reach the lower threshold, the person that was supposed to come and do maintenance, so refill the oil tank, was called. But for instance, think about it, if that would happen on Friday, the machine needed to be down the whole weekend, and maybe the person would be called on Monday or even Tuesday. So the goal, and also as mentioned before, so the data about the oil level was just present locally at the plant. So the goal for us, for our collaboration, was to, on one side, try to predict when the oil tank needed to be refilled, and try to set up an infrastructure so that it could be, all the data could be in the cloud, so that the information about when the maintenance needs to be done could be reached also from outside of the plant. And in this way, we were trying to minimize the downtime. So the architecture was quite simple. It looks like this. So we made use of the Azure cloud. So we have here at the side, we have our press, and the data were gathered thanks to some sensors on top of the machine and the control system of the press. The data were gathered and saved in an SQL database right on site, but they were continuously sent to the Azure cloud, and in the Azure cloud the data were cleaned, processed, and the machine learning models were run, and the prediction were done in the cloud. Once the prediction were done, they were sent back to the location where the data could be nicely displayed so that people could have a proper overview, and also the maintenance personnel could be timely notified if the oil tank needs to be refilled. What kind of data did we have? As I mentioned, the data were collected using sensors that were on top of the machine, but also using the central press controller system. And you have here in this picture an example of it. So, pardon. So this little box is the central controller that is sitting very close to the press itself. The main data we had were the level of oil and the temperature of oil, and these were taken thanks to a sensor that was floating inside the oil tank. But we also had a lot of information about the schedule of the machine, for instance, when the machine was running, for how long, which kind of work it was doing. And initially, when we started our use case, we had just a couple of months of historical data, but the sensor is gathering data continuously. Every other second, almost, we get information about the level of the oil and temperature. And this means that we had a continuous stream of a quite large volume of data. Just to give you an impression of how the data look like, here we have on the y-axis the level of the oil, and the time on the x-axis, and you can see it's like a seesaw. In particular, you can see in like this sharp increase going from the lower green circle to the up circle is when the oil tank was refilled. So the oil tank was refilled, then the oil level would go down slowly, and then once it would reach the threshold, would be refilled again, and so on. There are other interesting features that you might notice. So, for instance, the plateau that is pointed thanks to the red arrow, that is this plateau is given by the time when the machine was not in use. So when the machine was not in use, actually the oil level would stay constant. Other interesting feature are those spikes that, for instance, are highlighted by the red circle. That are just spurious signal that comes from the sensor itself. For instance, if the sensor, when the machine was in use, it would just tremble a lot, or just have movements, and the oil might go down below the level of the oil and therefore give some false signal, or for instance, it would get stuck on the side of the tank and then just give some random values until it would just start floating again. And please.
Thank you very much. So then, as you saw the data before, the most important part was, of course, understanding the data and cleaning the data to prepare it for the machine learning model. So the steps that were done was, on the one hand, removing known downtime. So this was such as weekend, holidays, but also when the machine was not running every single day. There were times in between that could be seen before just as flat lines. Those were completely removed. Also, the data collected every second was aggregated to be hourly, as there was quite some bouncing in between depending on the vibration of the machine and the oil level. So we saw that aggregating everything once per hour gives better results on this, and for here, just the mean value was taken. As the sensor noise can severely alter the resolution, then also those points with high disturbance needed to be removed. One way for this was then detecting the upper and lower bound of the two values, and then the lower one was in this regard taken. And for training, it was important to find then the refill dates. So for this, we smoothed still everything with an exponential function, and then selected areas with large increase. So when we had it at the bottom, and then the top one, and then we were taking the top one as the date of the refill. The refill itself took several couple hours, but it was just seen as a spike as the oil sensor was not measuring at this point. And then how do we detect all the disturbances, all the anomalies? There are different techniques that could be applied. So we had interquartile ranges. So basically, you have a band around your data, and everything which is outside can be flagged. You can see, does it work? And in red, you can see certain points of disturbance. But as you can also see, one approach is not perfect, does not show everything. There are still some spikes on the side here, or other points where the sensor might be stuck for several hours until, through the vibration, sensor gets loose again. So various techniques had to be applied. Interquartile range was working best. Otherwise, standard clustering approaches, or also local outlier factors would also counted, and isolation forest. Isolation forest is a bit different in this regard, as it just uses a binary tree and can give you, with very low computation intensive approaches, already outliers. And when we could identify the outliers, we were also classifying them and were notifying the relevant people, so the plant manager, what is most likely the issue and what action would need to be taken. So increasing oil level when the press is on is an anomaly, also decreasing when the press is off. So this is that most likely there are leakage which need to be taken care, large variations in general, but also on the temperature. So the temperature sensor itself had quite a lot of variation within the band. With the data we had so far, it was not possible to extract information out of the variation, but in the general trend of this temperature was important, and then also for certain thresholds, plant manager could be notified. And now the machine learning model, so what was actually used for the prediction. There are also several checks on models where we tested. It were some more complex models, such as long short-term memory models. But in the end, multiple linear regression, so very simple linear models, turned out to actually have almost the same performance as very complex models. But those simpler models also had the advantage of being very fast to train on, and then we could apply almost real-time predictions. So what was done for this approach? We were training on the historic data, and we were taking the last 30 days after each refill, and then calculating always the closest date. So if I'm, for example, here, the closest date is here of the refill. If I'm here, then it's here. And if I'm somewhere here in this realm where there is no closest date in the future, then this is the part I can use for the prediction. And then always taking the last 30 days, training the model on this, also including the oil temperature, as if the oil was changed recently, and new oil has usually a lower temperature, and then also could be used longer in total for the machine before it needed to be changed fully, rather than if there was only partly something refilled and the overall oil was a bit older, then temperature was higher, also it was harder on the machine, so also those had to be taken into account. After every refill, the model was retrained on the last 30 days, and then the prediction could be updated hourly. And the result in this regard could be written straight back into the SQL database we used, and the plant manager could see almost in real time the next prediction date. So the whole procedure of predicting was just done within minutes. So every hour, but later, they could see when the next estimate is, if it's 3 days, 4 days, 6 days, and then they could plan scheduled maintenance, plan that a downtime, and yeah, do this. And for the results, so we were able to implement successfully a scalable architecture on predictive maintenance. Here it was for one plant to predict the next refill date in days, so it was data-driven planning process that just showed more stabilities. On top of predicting the next refill date, we could also classify anomalies. And over the project itself was just a several-week project, and then now the project is running for almost 2 years now. And in this time, several anomalies could be detected, and then action could be taken, which otherwise most likely would have been an unexpected downtime, which is quite costly. And now, after gaining this information of this 2-year period, Magna decided to use this architecture to deploy it to other plants, so then also that when their transfer passes can use the same machine learning model, and cost saving will be even higher. And the relevance for your company, or in other words, why should I care? So if you want to save money, then you need to act at the right time, ahead of time, before the machine breaks, but also not too early. Constant maintenance is a lot of downtime, also costs repair money, so really knowing when to act, where to act, and how to act. This is key, and predictive maintenance can guide you in this regard. Unfortunately, no solution can fit all. It's not plug and play. So really having the business knowledge is very critical, working very closely with the business team, having the data scientist and the business team align. So kind of having translators between the two domains to understand what are the issues, why can be a sensor several hours have faulty readings. Naively, you would expect the sensor is broken, but knowing that it's floating, could be stuck in the oil, absolutely makes sense. So really this close alignment, but then not just close alignment, but also having the mindset of having data-driven approaches is crucial. Having decades of experience how the plant runs is absolutely crucial, but then also knowing when it might still make sense to trust the data is also something that takes time to change, but is a very important factor for the overall success. And just plug and play doesn't work, but the concept, the architecture is something that can be transferred. So important is transferability, the scalability, that what we have here in the cloud could easily be deployed to several other plants. And also once more plants come into play, machines might have slightly different, then even more important is the automated tests, or also MLOps. So the machine learning, the operation, bringing this together. In general, having all the experience from decades of software development, test-driven approaches is very important in this. And once you have your solution, you invested the money on one plant, gained the experience, then you could expand to several new plants and could so save even more money. So start small and expand is key message that we could do. And also important is predictive maintenance is not something that only works if data was collected for decades or several years and so on. It always depends on the use case, but in this regard, only this couple months possible to already start seeing savings on the cost factor. So what is the takeaway message from us? Predictive maintenance is crucial in today's ever-changing industry with even more complex interlinked processes. Then business knowledge is absolutely decisive for the success. Then the successful implementation of a scalable architecture is important. It doesn't have to start massive. It can start small, but have the concept in mind. Then it can easily scale to new plants and everything. And with those scalable solutions, further increase in profit and savings is possible. Thank you very much.
So, thank you so much, Simona and Johannes, right?
Thank you.
It's impressive. It's not a startup company, right?
No.
The Magna or ours?
Company,
no, definitely not.
It's not a startup company,
No.
but it's a strong software company. We saw yesterday some startup companies, a little bit more small companies. You have deep experience in these cases, I think, so as you present. Have you some questions out of the audience? Okay, from Ford.
Have you done only oil level analysis? Because in the press there is a lot of other downtimes, root cause. Have you analyzed different other downtimes, how you can improve?
Yes, there were also other.
Go ahead.
Sorry?
No.
Okay. Yes, we also looked into other kinds of data, so mainly vibrational data, which was also downtime from the motor itself, how it worked, and also here it was possible to get first successful predictions out of this, but in this regard, as the vibrational data had quite a lot of changes in between, just a couple of months of data was not sufficient, but now after running everything for almost 2 years, there's also a discussion to dig deeper into this regard and then also incorporate more sensor data to also be able to predict other downtimes, not just related to the oil level.
Yeah, I think you can get much more if you have all this downtime data, and also if you abnormality detection, then you can also document what is done with the abnormality. Was nothing, then you need to improve your models. And if it is done something, you document it and you use this data again to improve your process again.
Yeah.
Absolutely. Yeah. Sorry, I apologize. No, it's just like reiterating what you just said, and also what Johannes mentioned, that at the beginning we had just a couple of months of historical data, and unfortunately, mostly for the vibration, there was no anomaly in that data at all, so it was not that straightforward to predict what kind of possible anomalies there could be and what could possibly cause downtime. But as just mentioned, since now we have a couple of years of data, it is indeed possible to check when there was an anomaly, flag it, and then retrain the model, have a more comprehensive model, also taking into account, for instance, the temperature of the oil on top of the machine, and then try to take into account different kind of measurement for the whole machine.
I think important thing is if some people think if you have model, it's finished. But it is starting point. That is important. Okay. We learn a lot also, our data analysts, to do something and then they don't care anymore. But then it is not improving. So that need to be always with the new learnings, new data. It need to learn, and then it is improving continuously.
Yeah, absolutely. So this is also that the reportings and findings that we could show to the plant managers, that everything needs to be recorded or is recorded, and this is something where even more insights can be taken from.
Okay. I would like to give something to that in addition, right? As we discussed yesterday about that. I have strong experience in the case of product development, okay, over the whole range of to-dos. And in different kind of times, I'm very not successful if I don't pre-invest in deep cases of physics, chemicals, and so on, to be later on quite well successful with flow meters in any case of application. So what is the conclusion out of that? You must pre-invest something in your life to get results later on. And sometimes this kind of pre-invests are going into air. But you must do this to get out of it quality and so on. If you don't invest something in these cases, in pre-cases, then you have no success stories in any case later on, I think so. So one question from my side, you are a strong software company, right? Education of young people, you know, if I'm looking around, I have two boys, 20 and 22, and I said to him different kind of times, be software developer. And both said to me, no, Dad, no. What is your feeling? What is your impression out of the education in Germany, in Europe, to be strong in these cases, to force software competencies in Europe?
I think that there are several factors to consider. So one part, just let's say on Adastra side, so we try also to go close to universities when they have some open days, try to present our company, our use cases, what we can do to see if people want to start working already at us as student trainees. We offer bachelor or master thesis that they can be done in collaboration with us. So really bringing people during university already to industry, see what is going on, what is needed, and then they can learn from the beginning actually what steps need to be done for robust software development. So all the training, all the testing, everything is already considered from the beginning when they learn. I think this is very important to get lots of young people, but then in general, not just on our company, but software development, coding in Germany. I think it picked up in the last couple years that it becomes also in that school a bit more, but there's definitely still way more to go as other countries. They start almost in elementary school with some very simple coding, and here it's still just at the later stages, and unfortunately still how the coding is brought to the kids might still be a bit dry, and I mean I think that's not what coding actually is. Of course there are complex mathematical solutions, but finding the concepts, dealing with the problem, this is where the beauty lies in that.
Perhaps with Lego.
Perhaps with Lego.
Yeah.
Okay. Right. Any other questions from the audience? Okay. Thank you so much. And
thank you for having us.
Thank you
very much.